Right, so now we are moving on to section 2.3. We now have the atomic spectrum and the Bohr model. So, when atoms absorb energy from heat, light, or electricity, they often emit that energy as light rather than emitting electrons. So, for example, these are some elements that are passed through glass tubes. We have mercury, helium, and hydrogen. And actually, depending on the element, we can get different colors, and that is how neon signs are actually made. The neon runs through the element neon, and it causes it to light up a certain color. So here we have the emission spectra. So the most common way it's seen is through a prism. A prism will separate the wavelengths of light that first goes through it, and depending on what kind of lamp or light source that goes in, it'll only go through at a certain wavelength. The prism can only separate the component wavelengths to a certain point. So here we see helium, and the helium spectrum only goes on these colors. And then we have barium, and the barium spectrum is a lot bigger. The prism is able to separate out a lot more wavelengths, and basically the paths the electron takes. And then we have the white light spectrum. So when white light passes through it, white light is actually not just white, it is actually all colors wrapped up in one. And just as a reminder, this is normally what an atom looks like. We got the nucleus in the center, then we have the electrons orbiting, and the electrons are actually not orbiting this nicely. We can't actually predict where they are. We just know that around this little dot, the nucleus, they're just somewhere in kind of like a shell. They're just somewhere in this sphere around the nucleus. And with these n numbers, we can actually use the Bohr model to determine the wavelength of these bars of light, or these little bands of light, and we can calculate the velocity and thus the energy for each as well. An excited atom or electron does not emit light, so electrons moving around the nucleus in a normal fashion won't emit light either. So where does this light really come from? Well, in this model, electrons give off light when they go from a higher energy level to a lower energy level. So it's kind of like when you're super, super excited, you go to, let's just say, for example, what they used here, which is n equals 5. That's what that is right there. And so we go all the way from the second sphere around the nucleus where some electrons are, and the electron will get so excited that it shoots all the way up out to the fifth sphere around the nucleus. And as the electron relaxes, it will release energy, allowing it to relax to the second sphere, and the distance it travels here, or basically the velocity, will give us 434 nanometers, or it'll give off a blue-violet kind of light. Same here, going from 2 to 4, it'll give us 486 nanometers, which is blue-green or turquoise. And then just going from 2 to 3, we'll go all the way over here to 657 nanometers, or red. So going back to the question, again, where does this light come from? Electrons give off energy in the form of light when they go from a higher energy, or further from the nucleus level, to a lower energy level. Electrons are very happy and very calm when they're closer to the nucleus. Electrons are never found in between different energy levels. Whenever scientists would look at where electrons could possibly be, there was kind of an empty space in between. They were only in these kind of orbital areas. So when an energy hits an electron, it promotes it to a higher energy level. Then, when the electron relaxes back to its original or even other lower energy level, because it might just release even more, and say it started at 3 and then it goes up to 5 and then it could relax back down to 2, it gives off energy as a form of light. And depending on the distance traveled, you can get different colors in the form that they're basically described as nanometers. You know how some colors are described by like RGB values? Well, we could actually determine different colors based on the wavelength in nanometers. So for atomic spectroscopy and the identification of elements, it's kind of like a barcode. We can see that when, kind of the same thing as when we took the barium spectrum and we used it as a lamp and we emitted the light from that element through a slit that hit the prism, and the prism will separate it onto a photographic film, which will give us our spectrum. These kind of work like barcodes, and we can actually use them sort of like that for the elements. So for oxygen, this is its own spectrum. It's kind of, each element is going to have a unique spectrum, and this is the one for neon. Neon has a huge wide variety. It's why we have so many different kinds of neon signs. And we can even take it a step further when we do different types of atoms being burned. It creates different colors, and this is how we got fireworks. The absorption of light can also be used as a barcode for different elements, just in general, with different emission spectra and absorption. So where it absorbs light is kind of like the same as it emits it. Emitting, like giving off light, and then absorption, as it will only absorb certain types of light. So that might be a little bit easier to see. Next, we have the wave nature of matter, the de Broglie wavelength, the uncertainty principle, and indeterminacy. The Bohr model does a very good job describing small atoms like hydrogen and helium, but begins to fail when describing larger and larger atoms because there's so many spheres going around. You get n equals like 5, 6 up here, but there's a bunch of different orbitals in between as well. They just get so large and going in like different direction, like the XYZ planes, that it's actually really hard to even make a proper Bohr model, and it's really hard to look at it. This is due to the wave nature of the electron, which isn't accounted for. Only the particle nature is included. So if you remember the two-slit experiment, sometimes the electrons, when they pass through a slit, will form a wave-like pattern and get brighter in the center, and then slowly get less and less bright in kind of like bands off to the right and left. Whereas for particles, when it passes through the prism, it'll hit as different colors along the spectrum. So the Bohr model is only looking at the particles, but an electron is actually both a particle and a wave, kind of the wavy form of energy. And this is exactly what I was saying with the two-slit experiment, right? So the Bohr model focused on particles. There's only two bright spots here, and actual electron behavior is kind of an interference pattern or a wave-like pattern. But when we look at electrons, this is what they look like. They act like particles. And then when we're not observing them with some sort of instrument, we're just observing them with our eyes, then they have a wave-like appearance. So the entire interference pattern remains, even if the electrons are fired essentially one at a time, suggesting the wave nature of electrons. So the de Broglie wavelength is the wavelength of electrons is proportional to their kinetic energy. The faster the electron is moving, the higher the kinetic energy and the shorter its wavelength. So again, the faster the electron is moving, the higher its kinetic energy, it's going faster, and the shorter its wavelength. So it's basically not going like this, like it's not big waves, it's like really short waves. So this is a very important equation that you guys are going to have to know. It is the wavelength, which equals Planck's constant, and that is Planck, Planck's constant, divided by the mass times the velocity. Oh, sorry, this is the velocity, not the frequency. So note, mass times velocity is momentum. So it's basically the mass, it's basically Planck's constant divided by the momentum. And Planck's constant, because it's a constant, will always be one number. I think it's 9.02 times something, I think. But knowing the velocity or the wavelength of an electron tells you the other. So if you know the velocity, then you could get the wavelength. And if you know the wavelength, then you know the velocity, because you will always know Planck's constant. And even with the mass of an electron as well, because the mass of an electron will always be the same as well. It's not going to change it's not going to change depending on the element. The mass of an electron will always be the same. So this is an example problem that you guys should do. It is calculate the wavelength of an electron traveling with a speed of 2.65 E6 meters per second. Remember, E6 is 10 to the 6. So using our equation here and Planck's constant, oops, I was wrong. It's 6.626 times 10 to the negative 34, E negative 34 joules per second. 1 joule is 1 kilogram times meters squared divided by second squared. And then the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Given these two problems here, go ahead and try to calculate out what you get. And if you think you got it right, you can go ahead and leave a comment, and we'll see. So with the uncertainty principle, if you place the laser beam just behind the slits, it allows us to detect which slit the electrons goes through, but then it eliminates the interference pattern. So that's what I said, when you actually use something to observe the electrons, it'll turn it into particles here. Thus, we can never see both the interference pattern and simultaneously which slit the electron is passed through. The wave nature and particle properties are thus complementary. That's very important to know. This phenomenon is known as the Heisenberg uncertainty principle, which states that we cannot measure both an electron's position and velocity at the same time. Measuring the position changes the velocity, and measuring the velocity changes the position. The more accurately you measure one of these properties, the greater the error in the other property. Just like Schrodinger's cat, which is both alive and dead, just like last video, until we open the box. The Heisenberg uncertainty principle says that an electron is both a wave and a particle until we observe it. So next, we got, in our everyday world, which is controlled by Newtonian physics, you can know the velocity and location of an object at the same time. Likewise, two identical objects in the same experience or the same situation will have the same behavior. So here we have the classical concept of trajectory, which is just a ball thrown like on a baseball field. We have the arc of the ball, and then right here where the ball is right now, there's a force on the ball, which is gravity, and as the ball falls here, the velocity is continuing forward, so it'll like slap into his mitt because there's still like velocity on it. Same thing like when you're driving in a car and the brakes get slammed and then you jolt forwards. That is because you still have velocity even though the car stopped. So because electrons behave both as waves and particles, they kind of behave differently here. So as particles, they're still going to be on this like what's called a quantum mechanical probability distribution map, which is a pretty big thing, but basically it's a dot map of the trajectory. And then we got our little classic trajectory here. So at this time, the electron is more likely to be here compared to here. So it's more likely to be towards the center than it is going to be on the outside. It's in both locations or somewhere else unless it's observed though. So it's kind of like it'll be somewhere, it'll most likely be in the center here, but depending on if it's looked on or not, it might just be anywhere. So thus the location of an electron at a specific time is only a matter of probability. It is statistically more likely to be in one place over another, but it can be in many places at once. This is defined as interdeterminacy. I think I said that right. So defined as interdeterminacy. So it can be in many places at once, but it is statistically more likely to be in one place or another. So an electron is more likely to be in the center line than it is on like the outside in these little areas here. So unless it's observed, it's going to be in technically both locations. A fun thing, as this kind of gets into quantum mechanics, my inorganic chemistry professor basically once told me he held up an expo marker to the class and he said, this expo marker has a bunch of atoms in it. There are electrons around those atoms. He says in quantum mechanics or like even in quantum theory, the electrons around that expo marker are as likely to be hanging around the expo marker and super close as they are 2 towns over. So the electron might be around the expo marker or the electron might be 2 towns over, which is kind of ridiculous. But it is kind of a good example of that quantum theory and quantum mechanics are kind of crazy. But as long as you are looking at the bare bones and you keep thinking of examples, you're going to understand it and you're going to be okay. So there might be a lot of big words in here, so I strongly suggest writing down those problems we covered. And if you don't know any words, then take a deep breath and go ahead and Google them, or even ask something like ChatGPT. It is perfectly all right to go look up as many words as you possibly want and even like write them off to the side of your notes. So that way when you go back, you can remember and you can have them all right there for you. It is perfectly all right, because then when you forget again in the future, possibly, then you can go back, and eventually you won't need to look back if you keep having it handy and you keep seeing it. So all these different titles right here, like the Heisenberg uncertainty principle, make sure you're noting that down. Anything in red, make sure you're noting down. And overall, make some sketches and make sure to look up things and go ahead and practice those problems. And you're going to do great. I believe in you. See you in the next one.